Hello, Supercomputer 20 virtual attendees. I'm Mike Matthews, and I'm here to tell you about an algorithm that estimates the meteorological visibility from camera images. I first want to say that the development of this technology was significantly aided by the folks behind the Lincoln Laboratory supercomputing system. LLC, as is known, provides our developers with the ability to store large amounts of data, but more importantly, to rapidly process millions and millions of camera images to develop and test algorithm concepts. Before I tell you about the algorithm, though, let's look back at the history of weather observing, and more specifically, visibility. When weather observing first began, observers would at regular intervals go outside and take note if certain markers were visible. These markers were things like mountain ranges or buildings. Through experience, these observers would learn how to estimate the visibility in ranges that perhaps they did not even have markers for. With the need for manpower, though, these observations were very sparse, as depicted here in New England in the 1970s. In the 1980s, technology allowed for the development of the Automated Surface Observing System, or ASOS. This was a suite of sensors that measured all the required meteorological parameters. The visibility sensor, as shown here, uses a reflection of a laser beam over a 1 meter distance. It was possible then to expand the network of observations to locations with both power and communications. However, these systems are very expensive to purchase, operate, and at times, well, they do not equate well to human-based observations. And this is mostly due to the short distance over which the scatter of light is measured. And this leads us to today, where most Department of Transportation in many states, plus the FAA and other government entities, have installed thousands, perhaps millions of cameras to watch road conditions and provide pilots with a live view of the weather conditions. The density of the system is significantly higher than any traditional meteorological observing system. But currently, the cameras are only for viewing and do not provide any automation and reporting of conditions. To provide automated visibility reporting from camera imagery, Lincoln developed the Visibility Estimation through Image Analytics algorithm, which uses edge detection to determine visibility. To demonstrate this concept, we have identified 3 pixels in this image that are known distances, and compared that to the strength of the pixel edge with a co-located ASOS sensor. As you can observe, the green line associated with a marker that is a half mile away, and compare that to the normalized edge strength, that visibility increases as the edge strength increases. Typically, the edge strength is about 1/3 of its full strength at the range that corresponds to the distance to the marker. This can also be observed in the red line for a marker that is 3 miles away. For the furthest marker in the image, located on the horizon at 20 miles away, the edge is not visible when the visibility is below that distance. Therefore, we can develop a relationship between edge strength, the distance to a marker, and the overall image visibility. But of course, all image processing has its challenge, and that must be resolved. For this algorithm, the challenge is to only identify edges that are persistent and can be related to visibility versus the edges from transient objects such as clouds, vehicles, planes, and people. To solve this problem, we have developed a method to create a composite image over a multi-day period to remove the transient edges. But of course, the scene can change due to seasonal variations such as snowfall. Therefore, the composite image must have a limited time period to allow it to adapt to these changing conditions. It was also desired to develop a methodology that would not be camera dependent and could be easily dropped into a new camera installation. And finally, we know that solar glare is a huge problem for this technology. So we have developed techniques to combine multiple cameras located in the same location into one visibility estimate. As usual, the algorithm flowchart shown here can be complicated, but let me focus your attention to the 2 main components of the algorithm. First, across the top is a depiction of the composite generation process. The algorithm saves a history of images that are deemed clear data images, and then on a daily basis creates a composite and identifies the most prominent edges to create a clear edge mask. Next, the algorithm takes into account each new image, and in this case showing both a clear data image and a low visibility image, and compares the overall edge strength between the composite and the new image. This edge strength ratio is then translated into a visibility based upon the relationship that has been identified over a very large multi-image historical analysis. I also told you earlier that the challenges in individual images can be mitigated through a multi-camera system. Our algorithm includes a method to combine any number of cameras together into one estimate based upon citing information in the sun's position relative to the camera. Shown here are 4 cameras at a location in Alaska on a clear day. One of those cameras, one looking northeast towards the sunrise, is significantly underestimating the visibility at 1/2 mile, while the cameras facing west and southwest are estimating visibility higher than that at 10 miles, and that is the limit of a traditional system. In some installations, the capabilities of individual cameras may be limited due to a lack of edge markers or the overall conditions, such as having a tower blocking the camera. On the rock curve shown here for each of the individual cameras, you can see the performance varies. But after combining these cameras into one estimate, as shown here in red, you can see a significant improvement. To finish up, I would like to share with you a movie loop of the cameras at this location, the visibility estimate of each individual camera, and the combined results versus a co-located truth sensor. You can observe that the individual camera estimates have a wider range of results, but when combined into the black line and compared to the truth line from the ASOS in the blue, the algorithm does an excellent job estimating the visibility, and perhaps even more importantly, the overall trend during a low visibility event, which would be very important to pilots, transportation operators, and weather forecasters in general. Thanks for joining me and learning about the visibility through image analytics algorithm. A big shout out to the Lincoln Laboratory supercomputing team, and in the near term, if you would like to look and check out the performance of the algorithm, go to weathercansplus.faa.gov.